Okay, just want to give a basic introduction to text mining so that this is not at all comprehensive. It only deals with a very small part of text mining, but for what we're doing, it will give you some background. So here we have a slide. It's text mining, and it's related, we can see, to various other um, fields: data mining, information retrieval, web mining, computational linguistics and natural language processing, and statistics. And here's one picture of the text mining process, and we don't do all of these things, but and there are many different approaches to text mining because it's a new field and there are lots of different ways of proceeding. And the way that we're going to think about it is probably the most simple way, but it still can be effective. So it says up there on the left, document uh, here, document clustering and text characteristics. So we have the text here, and then we're going to do text preprocessing here, and a text transformation called attribute generation. Remember, in this case, attributes just means like think of it as variables, or at least that's the way I think of it. And attribute selection, so if you have a lot of variables, you might want to choose only the most important ones. And then after you've done all of that, then you do uh, data mining on it. And then of course you might want to interpret your results and evaluate your results. Pardon me. Document clustering. So this is one thing that you could do with in text mining. So one thing you could do is cluster the documents. So in other words, if you have many documents, you could try and group them into similar documents. And that's one task that you might do within text mining. It's not all of text mining, but it's one thing you might do. You might take a bunch of documents and group them into ones that are similar. So they say large volume of textual data, billions of documents must be handled in an efficient manner. No clear picture of what documents suit the application, so you're not really sure which documents you need. So you can use document clustering. What they're suggesting here is that you just clustering. You don't have what we've called in the past a you don't have what's called labeled data, or you don't have a class variable. You don't have something that you're trying to predict. You just have these documents. You're looking for looking for patterns within the documents, um, and so you want to just sort of group them. That's all. Most document clustering methods, most popular ones are k-means and agglomerative hierarchical clustering. So these are just different ways that you could cluster. And k-means, actually we're not going to go into this because we do it elsewhere. But alright, let's just read it. Given you have a set of documents, and what we're going to see is you get what's called a vector representation of the documents. And a suitable distance measure, the cosine measure we might use. And we might talk about that because it's interesting, but you don't have to do it that way. And the k is the number of groups. For each of k groups, initialize a centroid with a random document. So this is just the k-means, but using documents. Maybe we shouldn't talk about this here. So I guess when you do text mining, you have to think about what you're using it for, who's the audience for it. And some of the problems that you have are ambiguity, word ambiguity, and sentence ambiguity. So words have different meanings, and sentences can be interpreted in different ways. I think they give an example here. Also, noisy data, erroneous data. So, for example, if I show you the text that I'm going to give as an example, I'll show you that right now. This is just tweets from Twitter. And each row here is a different tweet. So if I click on the first thing here, I can see Michelle Obama. So this is obviously not English. So that's noisy data. That's an example of noisy data. And here's another one. If I click on this one, Michelle Obama brings toys for tots from the White House. Okay, there's not too much problem there, but this could be considered noise, I guess, here. The next one is what? Laugh out loud, RT, da 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 da. So some of this maybe you'd consider as noise or maybe not. Okay, here's another one. Post, Michelle Obama denotes to toys for tots. So because of the way this was transcribed here, I guess this would be considered noise. Okay, this is the data that I'm gonna give as the example. Each row is a tweet, and you'll notice that actually there's here's the first row here, and actually this all of the tweet is in the first cell of the first row, right? It's not in. If I click here, you can see it's empty, right? If I click here, you can see it's empty. All of the whole comment is in the first cell. Same thing here. The whole comment is in the first cell. Nothing in the second cell. In column B, in other words, there's nothing in column B. Okay, so there's noise, and you have to deal with noise. Noisy data, erroneous data, misleading, intentionally misleading data. Might be like that. Unstructured text. So this is unstructured text, these tweets, because a structured text would mean like if you fill out a form where it asks for your birthday and you say month, year, and date, and your name and address. So that's called structured data, okay, or structured text data still. If you give your name, that's text. But unstructured would be like these tweets or chat rooms or normal speech. High dimensionality. Well, we're going to see that. Actually, let's see it right now. Okay. So let's open up Weka, and I'm going to open that file. I hope it lets me open it. Let's see if it does. It's a CSV file. It's not an ARF file. It's not even there. Here. Okay, here it is. I want to do this. I need to do that because I'm going to need to force each piece of text to tell Weka that it's a string, and this is the easiest way to do that. So because when I click open, it's going to give me another dialog box where I can tell Weka that each row is actually a string, or I should say, that the first column of data, remember there was only one column of data. I made that clear. There's nothing in column B or C and so on. There's only one column of data, and I want to tell Weka that where the string data is, which is the first column, so I need to tell Weka that. So I'm going to do that now. Okay, and that's where I've used this. So it's the which attribute, which of the attributes are strings, but there's only one attribute, there's only one column. So I just need to say column 1 and click OK. Okay, so it didn't give me any errors, so everything is all right. Now I wanted to show about the high dimensionality, what they mean by that. So what that means is that in data mining, let's see if I go back to here and just open a new spreadsheet. So in data mining, usually what you have is along the top, you have the variable names, and then down here you'll have your data, your records. So you'll have like a variable one. I guess this would go here. Variable one might be like wind speed, and the next one might be humidity. How do you spell humidity? Is that right? And the next thing might be temperature, right, and so on. And then you'd have, okay, so for the first record, the wind speed was 2, and the humidity was 4, and the temperature was 44 or something. And this was 2, and this was 4, and this was 66 or whatever. So you'd have your variables up here and your records down here like this. Okay? So in here, actually, I should have given a name to this column. Maybe in the first column I should have called this comments and moved everything down, but maybe it won't matter. Anyway, so like I said, normally you have the variables up across here. So when we say high dimensionality, we mean many variables. So here I only have 3 variables, so that I wouldn't really call that high dimensionality. If I had this many variables, I don't know, I wouldn't necessarily call that high dimensionality. But if I had like 100 variables or 1,000 variables, that would be high dimensionality. So it's going to turn out that when we do this, we're going to get high dimensionality. Let's continue with it. So we got it loaded in here. Now what we do is we use Weka's filtering, and the one that we use is the string to word vector. And if I click up here, I can see the options for this. So the IDF transform, if you want to find out about a little bit about that, you can click here and check the IDF transform. Sets whether if the word frequencies in a document should be transformed into this. Now you can look into this a little more detail, for example, by checking Wikipedia on this, and the TF transform that does something else. I'm just going to leave that for now, I think. Might not need to do that, either of those. Now here, I'm performing some function on my data, and which attributes do I want to perform it on? Well, I really only, there's only one, so I could leave it as first to last because that means all of them, but I could also just say attribute 1. This I talked about later, and I won't do it now. This I won't do. This is like, do you want all of the, well, let's forget about that now. And I talked about this later, so I won't talk about it now. Normalized document length. Now, output word counts, I'm going to say yes. And periodic pruning, I'm not going to do that. And the stemmer, I'm not going to do it, but we'll still talk about it a little bit. Stop words, I'm going to use the stop words. I think yeah. And tokenizer, I think I'll just leave that as it is. Okay, so I do all of this, and now I apply this to my data, to my first column of data, which actually contains all of my data. Now what does it do? Well, let's apply it. Maybe we can see by applying it. Apply it. and it's done. Okay, now you should know that in Weka, what you see in this area here is a list of all the variables. So like in that example before where I talked about wind speed, humidity, and temperature, if I was working with that kind of data, what I would see here is 1, wind speed, 2, temperature, 3, whatever it was. I mean 2, humidity, 3, temperature. And that's all I would see. 1, 2, 3, not so many here. So what does this mean? This means that Weka is now treating this as though there are many, many, many variables. What variables? Well, it's not wind speed, it's not humidity, it's not temperature. So there's like tots is a variable supposedly. Obama is a variable. Toys is a variable. Scrolling down here, hair is a variable. Inches is a variable, and so on. What are they talking about here? By the way, how many variables are there? There's so many. I didn't mean to get so many, but anyway, there are so many. 6,083. So if you agree that these are all variables, you would certainly call this high dimensional because there's a lot of variables. Okay, now what is this? Well, what it did was basically it went through all of these tweets, and there were, I guess, many of them. How many? 1,376 tweets. Okay. It went through all of those, and it just took all these words and made each one into a variable. Of course, if the word occurs twice, it only treats it as one only counts it one time. It only treats it as a single variable. For example, here I see my latest column. So column appears here, or latest appears here, and then it also appears here. So there will probably be a variable called latest, but there won't be two variables called latest. There'll only be one. And then I also had a setting there where I removed stop words, and stop words are just words like, let's see, 2 here, up here, right? So that's called a stop word, and we don't really want to include that in our analysis. Okay, so those are called stop words like to, the, at, and so on. So we remove those. So they hopefully did not appear in here, in this list here. Okay, so that's what we've done so far. We've gotten all those words. These are called tokens. We've taken all the tweets or each tweet, and we've tokenized it. We've split it up into words and removed some of the words, like the to, the, and so on. And then we are really treating each one of those words as a so let's see, can I copy that? I don't think so. No, I can't do that. But I could take let's see. So spicy, fries, favorite, blame, diddy, skull. So what am I talking about? I'm talking about this. Spicy, fries, what was it? Blame, diddy, and skull, for example. And then you just have all of them here. Okay, then what you have is like the first tweet, maybe it doesn't have the word spicy, so I'll put a 0. But maybe it did have the word fries, so I'll put a 1. And maybe it doesn't have this, so I'll be 0 there. And maybe it doesn't have this, and be 0 there. And the next one, maybe it doesn't have any of these words, so I'll put 0, 0, 0, 0, and so on. And maybe the next tweet had 0, 1, 1, 1, and so on. So, we'd have many columns here, and each row would be a tweet, and this would say whether this particular word, like blame Diddy, occurred in that tweet. So it did occur in tweet number 3, but it did not occur in tweet numbers 1 and 2, for example. Okay? And this is called I always get confused. I always forget. It's called the term frequency matrix, or it's called the frequency term matrix. I forget. But I think it's called maybe it's called the, I forget which one, but it's one of those. The term frequency or the frequency term matrix. I think one is just the transpose of the other. So, did we really get that? Well, Weka did that for us actually. After it, as part of what we did when we clicked up here, we said give us the frequency. Where is it? Da, 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 da. Where did I say that? Oh, output word counts. So give me the frequency. So it did that. Now I don't see it yet. We don't see it yet. But we can see it by clicking edit. Then it will show us basically the spreadsheet that I was just talking about. Since it's so big, it might take a long time to open it. I didn't mean to make it so big. Part of the options in there, part of the options in here would allow me to make it smaller, not so many words, but anyway, here it is. So here's the first word in our list, the second word, the third word, brings, the fourth word, house, the fifth word, Michelle, Obama, tots, toys, white, HTTP. So these are all the variables, and there are a lot of them. We said there are 6,000 of them. Now, this is like, I don't know why it's missing number 3. For some reason it's missing number 3. Straight. I wonder why some of these are missing. I have no idea. Anyway, that, I don't, maybe it can't, maybe this is just a sample because it's too big or something. I'm not sure. But anyway, so this is document number 26, and it doesn't have 0. I'm sorry, it doesn't have this word bit. It doesn't have this word add this. It doesn't have this word brings, right? It doesn't have that. It doesn't have that. That is, it doesn't have house, but it does have Michelle, and it does have Obama. Okay? Whoops, I just messed that up. So you can see how this works. Now, so you can also see that most of these entries are all going to be zeros, right? Obviously. So, because each tweet, tweets only consist of 140 words, so we have 6,000 different words here, so a tweet, most of these words will not be in any particular tweet. Oh, by the way, it also says here, for example, numeric, right? So that means that this variable is of numeric type. You'd say, well, why is this variable numeric? It means the values that it can take are here, are in these columns here, and they're all numbers. In fact, they're all zeros so far, but they could be ones, twos. Just depends how many times it occurs. So that's even though the word, I'm sorry, the variable looks like it's a word, looks like it's a not numeric, but really we're thinking of it as a numeric because we're just counting the frequency of that word. Okay, so by the way, let's just see something. What would happen? Let's do a little bit more here. Let's try this periodic pruning. That you can look up what that does. I think that will lessen the that might make the dictionary a little bit smaller, but this will definitely make the dictionary smaller. If you change this to this, and then minimum frequency, say 5, So what you're doing now is saying only include words that occur at least 5 times throughout all the tweets. So that's going to give us a much smaller dictionary instead of 6,000. A dictionary means the set of all the words that we get. So we got like 6,000, but this is going to give us a much smaller set of words. So let's try that first and see if that's true. So let's apply it. Didn't seem to be much smaller, strangely enough. Is that true? That's strange. I don't believe it. Let me try something out much stronger. I don't think it's working exactly the way. Let's see. Okay, and apply. Not working. What's wrong with that? Maybe this should be false. I'm not sure. Let me try that. No. I think I might have to, I'm not sure. Maybe I have to reload the data. And I want to make this do not operate on a class basis. I think that should be true. And yeah, now it's so much smaller. Now we only have, I guess you had to reload the data. Now we only have 41. So remember I said I made 25. It had to occur in at least 25. That seems a little bit too big, too strong, too strict. Let's say 8. How many do we, but maybe it's not going to change now because maybe we have to reload it again. Yeah, it looks like we have to reload it. Anyway, so what we got here now is a much smaller dictionary. Okay? So these words occur much more frequently. So that might be useful, but that might be too strict. Okay, and by the way, let's look at the spreadsheet that was generated by clicking Edit again. Okay. So now we have far fewer words in our so-called dictionary. Okay, far fewer columns. Okay, now one other thing I'd like to show you. Let's open it again. Do this again. And this time let's change something. First of all, that's 8. Okay, maybe that's better. And let's change this to stemming, just to see what stemming does. So choose a stemmer. I think the only one that's installed is this one called the snowball stemmer. But you can learn about that later. So click OK. And let's see what we get now. How big is it? It's bigger. It's not a lot bigger, but it's bigger. Now, in terms of the stemming, did it work? Not so clearly. So maybe I can't show you so clearly what the stemming does, but we'll see that in this PowerPoint that I'm going to continue with now. All right, so that's the basic idea. Let's go back to that PowerPoint. So we said that it's high dimensionality and sparse input, right? We said that mostly zeros, right? That's what they mean by sparse input. There are mostly zeros in each row. Tens of thousands of words, and we're saying the words are the variables or the attributes. Only a small percentage is used in a typical document. For example, the top 2 words might occur in 10 to 15% of all word occurrences, the top 6 words in 20%, and so on. And they just do one thing that can certainly be interesting is to do a word frequency. Now, to get a word frequency out of Weka, you have to be a little bit creative, and it doesn't quite do it as easily as you would like, but you can definitely use that function that we just saw to do it if you think about it. Going back to the text mining process, when you get text, first you have to clean it up, and then you tokenize it, which is what we just did. We broke up the text. In this case, our text was a tweet into single words, and that is, like I said before, this is a very basic way to go about text mining. No, I'm sorry. Yeah, what we're doing is a very basic way to go about text mining, but tokenizing is used always. The next thing that we are not doing, which is basic, because we're doing it in a basic way, is we're not doing something, for example, called parts of speech tagging, where you try and name each word. What part of speech is it? For example, is it a noun? Is it a verb? And so on. But we're not doing we're not doing that. Word sense disambiguation tries to sort of get at some of the meanings of the words or something like that, and semantic structures. Let's see a little bit about this. So first of all, if you've got text, you have to clean it up. Like, for example, I had to collect this data, the tweets, and I also had to prepare it for Weka in various ways. Like, you have to get rid of extra commas and do things with apostrophes and quotation marks and so on. So that's we could say that's cleaning it up. You might have to remove ads from web pages, normalize text converted from binary formats, deal with tables, figures, and formulas. And then you do the tokenization that we saw, splitting up a string of characters into a set of tokens, stringing up a sentence or a tweet into a set of tokens or words, and need to deal with issues like apostrophes. You have to do that for Weka. Hyphen, sometimes that gives you problems. There are lots of different issues that you might run into. We don't do this, but maybe just look at it quickly. Text processing continued. Parts of speech tagging. The process of marking up the words in a text with their corresponding parts of speech. It's rule-based, depends on grammatical rules, so statistically based, so there are different ways to do that, but we're not going to do it anyway, but you might be interested in that. Word sense disambiguation, so determining in which sense a word having a given number of distinct senses is used in a given sentence. For example, this. The king saw the rabbit with his glasses. So if you think about that sentence, it could have at least two different meanings, right? The king saw the rabbit, and the king was using his glasses to see the rabbit, or the king saw the rabbit. Which rabbit? The rabbit that was wearing glasses. So at least two meanings there. So you might try to deal with that issue, and that would be called word sense disambiguation. Semantic structures means the meaning of the words. Now, we don't deal really with the meaning of the words at all when we just break it up into that big matrix. So they say there are two methods. Full parsing produces a parse tree for each sentence. So as far as I know, that just means that you're sort of putting the sentence and kind of considering its grammatical structure and making a tree from that. You can look that up. And then I guess chunking with partial parsing. And which is better? Well, we're not going to do either, so. By the way, sometimes they use the word POS, parts of speech tagging. I'm not sure what this is. So, attribute generation. So that's what we did when we created the matrix. using Weka, and we got many variables across the top, or as I said, a big dictionary. And each variable, each word rather, was a variable, and another word for variable is attribute. So we generated a lot of variables, we generated a lot of attributes. Text representation, text document is represented by the words or the features it contains and their occurrences, how often. Two main approaches of document representation: bag of words and vector space. Now actually I'm not aware that those are different. In fact, I thought they're the same. So if they are different, I'm not sure how they are different. Feature selection. Which features best characterize the document? So after we get that 6,000 set of features or dictionary, we might try and make it smaller and choose a subset of those features. And which ones should we choose? So I did make it smaller by saying that the words had to occur at least 8 times. And by the way, there was one option there. What was that? So one of these options, I forget which one, or I forget how to work it, which I think the way I've done it is right. When you do this, one of these, if you say true and you say 8, it means that if you say 8 and you say true, it means that the word has to occur at least 8 times throughout all the tweets. And the other way, I think it's when you say false, is that you have to get the word has to occur at least 8 times in a tweet in order to be in the dictionary. I don't think that's what it is, because I'm sure there are very few words that occur at least 8 times in any tweet. So I think I had it set the right way. Okay. So anyway, that's part of what's called feature selection. It means it's just selecting the variables that you think are most important. In this case, the variables are the words, so selecting the words that you think are most important. One way to do that is just in terms of the frequencies, having a minimum frequency. Actual attribute generation, that's what we did when we pressed the apply button and we got the spreadsheet. Use a classifier to automatically generate labels from the features we feed into it. That's a little bit different actually. So here's just another kind of picture of this. So we have Journal of Artificial Intelligence Research. This is a refereed journal covering all areas of artificial intelligence, which is distributed free of charge over the internet. Each volume of the journal is also published by Morgan Kaufman, ... So this is a document, and we can form a vector from this document, just like we did for each tweet. We formed a vector, right, of zeros and ones and whatever the frequencies were. We can do the same thing for this document. So for example, does learning occur in this document? Apparently no. Does journal occur? Apparently it does. 1, 2, 3 times. You can see 3 arrows. Does intelligence occur? Once and twice. Okay, so you get that. Alright, so this is called the bag of words representation. Let's see, do they do vectorization? Okay, let's see. Word weighting. Now, in the example that I gave you, for example, here, I only count. I used I counted how many times. So apparently in this tweet, this word blame Diddy occurred once. Maybe it occurred twice, so I would put a 2 there. Okay, so I filled out this spreadsheet using the frequency. However, I told you to look up some things on Weka, and you could make certain changes, and you could use a formula like this. And this looks a little complicated, but it's really not very complicated. This is the frequency that we just talked about here. Well, I can't select it. TF is the token frequency, I think, or no, term frequency. And DF is the document frequency. So let's look at this. So TF is how many times it occurs. That's what we were just talking about before, 0, 1, 2, and so on. And DF is not how many times it occurs in a particular tweet, but how many times it occurs in all the tweets. So maybe Michelle Obama occurs in every single tweet, all 1,300 and something tweets. So that means this DF would be like 1,300. That's how many times it occurs in all of the tweets or in all of our documents. Now, what are we doing though? We're dividing around here. We're dividing by this DF. So why is that? Well, the idea is that if the if the word occurs in all the tweets, then in some sense it's less important. In what sense? Well, this idea actually comes from what's called information retrieval theory. But anyway, in what sense is it less important? In information retrieval, what you're trying to do is distinguish between the documents. Because information retrieval is like what you do when you do Google, right? You type in a word and you're trying to retrieve information, right? So what you'd like is you want to be able to distinguish between the pages. Google wants to be able to distinguish between the pages and bring you the proper ones, not just all possible pages, right? So if something occurs in every page, then it makes that word less important in terms of distinguishing between the pages or distinguishing between the tweets. So the larger DF is, the less we want to consider that important. So we put it in the denominator. And N is the number of documents, and then the log just sort of transforms that in some way. So that's the idea of TF-IDF, and you can also look at this more carefully at Wikipedia. So I guess my vector space document representation is just a little bit different. Instead of writing that matrix that we saw, like this one, or the one that we had in Weka, instead of doing that, you could make the matrix a little bit different. I'm sorry, you could present the results a little bit differently. And because it's a sparse, remember we had so many zeros in each row and nearly no ones. So this is a way of sort of getting around having to write out all those zeros. So here we're not expressing any of the zeros. So we're just saying there was a word resorts, and that has a weight of this. And there was a word class, and that has a weight of this. So we're just writing out the words that actually did occur and telling their weights. It's just another way of expressing that matrix, but it's a little less, I guess it takes less computer storage space and also might be faster to search through. Okay? So what is feature selection? Select a subset of the features to represent a document. So you can do that you can think about ways to do that. One very simple way is just to do it in terms of the minimum frequency, which is what I suggested. Can be viewed as creating an improved text representation. I guess so. Why do it? Many features have little information content, whatever that means. Well, but in particular, of course, stop words have very little information content, right? Words like to, the, and so on. Some features are misleading, some features are redundant. Independence assumptions results in double counting. Some algorithms work better. So some algorithms, they mean now after you've created this big matrix, then you can do clustering like they suggested earlier, or you can do lots of other kinds of regular data mining on this matrix. And some algorithms work better with small feature sets. Stop word removal. The most common words are unlikely to help text mining, the, a, and you. Stemming. Okay, here's stemming. I didn't see it so carefully. I didn't see it so clearly when we did it, but this is what stemming is about. Identifies a word by its root. You can look up stemming, by the way, also, and look up Porter stemmer, P-O-R-T-E-R, Porter stemmer. In Wikipedia, you'll find a very interesting discussion of this. But anyway, it identifies a word by its root. Reduce the dimensionality, the number of features. So here's another way, apparently, to reduce the number of features, because what it does is it tries to do things like if you have the word flying or if you have the word flew, it's going to change them both to fly. So because really we can say they kind of represent the same concept, so why have two of them? Instead we can have one, and so every time if you have flying or flew, you'll count it as fly. So that might be a better approach. And there are two common algorithms for doing this kind of stemming. One is called the Porter algorithm, another is called K-stem. Let's just read a little of this. So here's an example, stemming examples. Here's the original text. Document will describe marketing strategies carried out by U.S. companies for their agricultural chemicals, report predictions for market share of such chemicals, or report market statistics for agrochemicals. Okay, so that's the original document. And then what does the Porter stemmer give us? Market strat car. So that's why I don't like to do this, because car, it's very hard to figure that car means carried. But that's what Porter stemmer will give you. Compan, I guess that's not so hard to figure out. Agriculture, I guess that's not so hard to figure out. Chemic, I guess that's not so hard. Report, predict, market, share, chemic, market, statist, agrochem. Okay, and the K stemmer, we'll do it like this. Gives you marketing, strategy, carry, company. Looks like pretty good, actually. I like that. Maybe I have to find that one. Chemical, report, prediction, market share, chemical, report. Oh, it's good. Except it says marketing and market. But anyway, that looks pretty good. Okay, then they say you might think about feature selection, like should you do it before you go ahead, after, later, as I said, you're going to do data mining algorithms on the matrix that you get. So we have this big matrix, and we can use that for data mining, like put it into a neural network or something like that. So should you do the feature selection before putting it into a neural network? So they say select features before using them in a classifier. Requires a feature ranking method, so you have to decide which ones to keep and which ones not to keep. And there are many choices. On the other hand, select features based on how well they work in the classifier. So you might sort of use them all, put them in the classifier, somehow figure out which ones were most important for that particular classifier, for that particular neural network, for example, or whatever data mining algorithm you're going to use. So figure out which ones were most important for that particular algorithm, and then throw out the others. So you can do this feature selection before or after. They say it's an iterative process. So I think that's all I'm going to talk about now. Yeah. So then they say afterwards, after you get that, you're going to do data mining on it. And I think I'm going to stop there. Okay, so that's the introduction to text mining. And well, let's just very quickly run through a little bit more. So we had just these not so many features here, and we could do some text mining on data mining on this. Well, let's just do one. I do this in other videos, but I'll just do it now, just to close this out. So I'm going to do clustering. Did they have that? I wonder if they have that k-stemmer. Stemmer. No. But you can add stemmers to this. You can add other stemmers to this. Anyway, let's do the clustering. Let's do the k-means clustering. Whoops. Let's do the k-means clustering. Simple k-means. Let's break it up into 4 or 5 clusters. And no. And just do it. Okay, so it's done. And it broke our tweets into clusters 0, 1, 2, 3, 4. That's 5 clusters, right? It broke it into 5 clusters. 1% of the tweets were in the first cluster called 0. 5% were in the second cluster. 54% were in the second cluster, the third cluster, and so on. Furthermore, you can also see here the these are in cluster 0, for example, go down to here, Barack had a weighting of this. Barack had a weighting of this in cluster number 2, had a weighting of this in cluster number 3, and had a weight. So basically, here, this one and this one are larger. So clusters number 0 and 4 had kind of higher weightings in terms of the word Barack. So maybe more about Barack. Now, by the way, all of these tweets were about Michelle Obama. Of course, sometimes it might mention Barack as well. Now, Catwoman had 0 weighting in cluster number 0, 0 weighting in cluster number 1, a little bit of weighting here, no weighting here, and a little bit more here. So apparently in these tweets, Michelle Obama went to a Halloween party, I think, and she was dressed as Catwoman or something like that. So maybe this last cluster is our tweets about that event, okay, to some degree. Okay, so that's what you get here. Another thing to mention, something to think about, is I just did the clustering on this matrix, right? Here's the matrix again. Let's get it. There it is. I just did the clustering on this matrix. Now, suppose I took the transpose of this matrix. So you know what I mean by the transpose means make each one of these a row instead of a column, and make each one of these rows a column. Okay? So just sort of flip it over or something. So that the rows become the columns and the columns become the rows. So then if you did, so then the records are the words, right? So now and we just before we did clustering of the records. So I found groups of records. But if I do it this way, if I take the transpose and then do the clustering, what am I clustering? I'm not finding groups of records anymore. I'm finding groups of words. So what does that mean, to find groups of words? I'm finding groups of words that are kind of similar, at least similar in terms of our data. So that would be an interesting thing to do as well. Okay, so you would find groups of words that are similar. And maybe you'd find groups of words that sort of point to the same thing. And maybe you might look at it one group of words and then say, oh, they represent some sort of general concept. Maybe you'd do this for like in 20 different clusters. So you might get like 20 different concepts. So this is a way of doing what's sometimes called concept generation or category generation. So you sort of go sort of one step higher than just the words to like groups of words that might point to a concept. Okay, so think about that as well. Okay.